Hi, my name is Yuri from the University of Massachusetts Amherst. I'm incredibly honored here today to be giving this keynote address at the Joint International Conference on Software and Systems Process and the International Conference on Global Software Engineering. The issue I'm going to be talking about today is of great importance. What you're seeing on the right side of the screen right now are examples of software systems that have been given the ability to make important decisions and have done things we'd rather they didn't. What I'm going to tell you about today is that discrimination bugs are very common in software systems, and I will discuss ways to prevent the undesirable behavior of intelligent machines. Do you recall the plot of the movie Minority Report? The police no longer investigate crime. They show up at the location where the crime is going to take place and prevent it before it happens. Well, in Los Angeles today, police are using software to predict likely future crime scenes and deploy there. The creator of the software was quoted as saying, "This is not Minority Report." So, well, it's kind of close. The main point I'm trying to make here is that globally, software is making some incredibly important, influential, really critical decisions. And when it's not making them, software is often influencing them. Unfortunately, we all know that software can be buggy and can do things we don't expect it to do. A few years ago, Orbit steered users visiting its website from Macs towards pricier hotels than those visiting from PCs. You could argue this makes some sense. Macs typically cost more than PCs. But you could also argue that the software was acting unfairly. Banks often use software today to make decisions about whose loan applications should be approved. In fact, you can apply for a loan online and get a decision almost instantly. Well, in America, a study found that minority home buyers face discrimination when applying for loans, both when humans review their applications and when software does it. So how do you measure this kind of discrimination? There are many confounding factors, and wealth is not evenly distributed in America by race. Well, one way to measure it is to look at profit the banks make from people of different races. This study found that African American and Latino borrowers are charged higher rates and that banks earn 11 to 17% higher profits off such borrowers than off white borrowers. So software can do unexpected things. Software can be buggy. And it turns out software can discriminate. My interest, and the focus of this talk, is a particular kind of software bug, software bias. And I'm also interested in how our processes, tools, and software engineering practices can help identify and remove such bugs. Let's take a look at how software bias might affect tools we use every day. Let me do a quick live demo. I'll head over to Microsoft Bing Translator. I'm going to translate two sentences from English to Turkish. She's a doctor, he's a nurse. Note that the doctor is a woman and the nurse is a man. I'll translate to Turkish, and then I'll translate the result back to English. Note that the doctor is now a he and the nurse is now a she. This, turns out, is not an easy problem to solve. Let's talk about another service we use daily. Everyone uses YouTube, right? We're even using it right now. When you upload a video to YouTube, you can select an option to automatically generate closed captions. If I told you that the accuracy of the captions will depend on your accent, you probably wouldn't be surprised. Folks from California will have lower error rates than, say, folks from Scotland. You might say that's not fair, but we can understand why that's happening. Probably there's a lot more training data from Hollywood movies with high-quality captioning. But would you be surprised if I told you that the error rates for female voices are nearly twice that of male voices? And I could spend an entire conference just talking about bias that's been identified in facial recognition systems. I have 4 goals in this talk. First, I will define what it means for software to discriminate. Then, I'll show how we can operationalize that definition to test software. Next, I'll demonstrate how we can limit the impact of bias in software. And finally, I'll describe how I can formally guarantee fairness in software. The first thing one might say is, let's just design software to be fair. And there's a lot of work out there that focuses on machine learning software, software that uses lots of data to make decisions. Fairness through design is important, but there are many possible causes of bias. For example, bias can come from the underlying data, or it can come from design or implementation bugs, unintended interactions, or even things like societal phenomena, such as that one gender is more likely to wear makeup than another gender, and that adversely affects facial recognition precision. Software design simply isn't going to magically address all of these causes alone. Even the best designed software today routinely has bugs. What we need are tools that detect bias in software that can inform both developers and users and helps developers improve the software. There are many possible causes of bias bugs. Learning from biased data is one of them. But poor system design could lead to bias as well. And bugs in the implementation can cause bias.
Imagine putting a minus instead of a plus somewhere, and that code happens to deal with a particular set of zip codes that correlate with race. Now you've got a system with a bug that affects users of one race more than another. And even unintended interactions between components can lead to bias bugs. A key observation I want to make here is that fairness is just like quality or security. To say that a software system has to be secure could mean a million different things in different domains to different stakeholders. The same is true for fairness. Depending on the domain and the stakeholder, fairness can take on many definitions. And you cannot simply take an existing system and make it fair after the fact, any more than you can make one secure. Just like quality and security, fairness has to be a first-class concern throughout the software engineering lifecycle. It needs to be part of the requirements phase, in part so that all stakeholders can agree on the goals with respect to fairness and how it might affect other goals. And we need to develop design principles that facilitate fairness. And, of course, if you want your system to actually have fairness properties, you have to be able to test those properties. I'll tell you today about how we can automatically generate tests for this purpose. And, finally, when possible, you want to be able to formally verify fairness properties and use verified components in constructing systems. Alright, let's first talk about requirements.
To do this, we need to define software discrimination. Let's start by looking at a simple program called loan. Loan's input is a loan application. For simplicity, let's say it consists of only 4 fields: income, savings, age, and race. The loan's program output is either approve or deny. Reasonable people may disagree about what is and what is not okay for a loan program to do. Discrimination is a loaded term, but you and I are likely to agree that it's okay for loan to discriminate with respect to the applicant's savings or income, but perhaps not with respect to race. This video isn't about the important questions about what is and what is not okay to discriminate with respect to. Instead, it focuses on the situation in which a company or a customer has decided the software should not discriminate with respect to a particular information and wants to measure if the software does so. You might say, why is race even an input to the loan program? Why not require age and race be omitted? Then the loan program cannot discriminate, right? Unfortunately, no. In 2013, Latanya Sweeney showed that searching for traditionally African American names on Google resulted in a higher likelihood of seeing ads for arrest records. Imagine a boss Googling a potential employee before an interview and seeing ads for arrest records. That might influence the interview outcome. But the Latanya Sweeney query doesn't include the race. It only includes the name. Google has fixed this specific problem since 2013, by the way, but the issue here is correlations between attributes. Without asking for your race or age, the loan program may infer those from your name, your address, the school you attended, and so on. In 2016, Amazon used an algorithm to decide where to enable free same-day delivery. For Boston, the algorithm decided to deliver everywhere except that one neighborhood in the center, Roxbury. Well, Roxbury is a predominantly minority neighborhood, and all the neighborhoods around are more affluent. You might say that happened by chance, but in city after city, the same thing happened. Amazon got a lot of negative publicity for this and manually overrode the algorithm. But a key observation here is that race was not a part of the input to the algorithm. But, in America, race correlates with zip code, and the algorithm found a way to discriminate. Now, we could talk about the underlying data and why this happened, but from a software engineering point of view, this is clearly not a property of the system Amazon wanted. They ended up overriding the system once they learned about it. Surely they would have preferred to have software engineering tools to at least test the system before deployment for such discrimination, and, ideally, to design and build it without discrimination in the first place. The idea of hiding the sensitive data from the algorithm is known as disparate treatment. It is even required by law in some situations, but empirical evidence has shown again and again that it simply does not achieve its goals. Let's consider another definition of fairness, demographic parity. This definition compares population proportions. In our loan example, if 35% of green people get approved for a loan, but only 20% of purple people do, the bias, according to the definition of demographic parity, is 35 minus 20, or 15%. However, this definition too has problems. In particular, it fails to identify discrimination against individuals. Let me demonstrate that with an example. Suppose our loan program gives loans to all the green people in Europe, but to none of the purple people there. In Asia, it does the opposite. All the green people get denied, but all the purple people get approved. If the number of purple and green people on the two continents is the same, demographic parity says this system has a bias of 0.
even though it is clearly discriminating against race based on location. Now, one might say that this is just a matter of defining your sensitive attributes correctly. If race and location were both sensitive here, demographic parity would catch the discrimination. Unfortunately, while my example made it really easy to see how to separate the groups to catch the bias, this is not typically possible. A notion of fairness gerrymandering demonstrates how data mining algorithms can slice data to create intricately shaped regions where the algorithm discriminates on one region in one way and on the other region in the opposite way. So the two regions cancel each other out. But those regions can be arbitrarily complex and cannot be easily discerned, unlike my Europe and Asia example. I have talked about two definitions of fairness, but there exist dozens more. Disparate impact is related to demographic parity, but looks at the ratio instead of the difference of proportions. Disparate impact is also prominently featured in some laws, but also fails to accomplish the goal of individual fairness. Delayed impact captures the notion that making seemingly fair decisions today could have vastly unfair negative consequences down the line for precisely the groups you wish to protect against discrimination. And there are many more: predictive equality, equalized opportunity, equalized odds, treatment equality, metric fairness, representation disparity, conditional use accuracy, accuracy equality. There are dozens of these, and each may be appropriate in a different domain, in a different setting, and for a different software system. Understanding these properties and when each is appropriate is an important part of specifying fairness requirements for a software system. But all of these definitions I have shown you so far suffer from a common problem. None of them would catch the Asia-Europe example I showed you earlier. And the reason is that these definitions, fundamentally, are measuring correlation between sensitive attributes and software behavior. And as we all know, correlation does not mean causation. What we really want to know is when sensitive attributes affect software behavior. We want to measure causality, which is typically very difficult to do, but with software, we're very lucky actually. We developed a technique called causal testing. Starting from the observation that what we want to measure is when sensitive attributes affect behavior, we can form a hypothesis and test it. Suppose green Yuriy fills out a loan application and it gets approved. Well, we have the software, and we can generate a loan application for purple Yuriy and run the software on it to see if the outcome is the same or different. If it's different, then, since the only difference in the inputs was Yuriy's color, we know that color caused the different behavior for this particular input. And we can do this for many inputs to measure how often this happens. Now, those of you who have worked in software testing know that it is relatively easy to generate inputs. The hard part is generating the oracle for the test. The oracle is what the test is supposed to do if the software is correct. If it weren't for the oracle generation problem, a lot more of our tests would be written automatically today instead of manually by developers and test engineers. But with causal testing, we're very lucky. We do not need an oracle. The fact that green Yuriy's and purple Yuriy's loan applications should result in the same outcome is our oracle. To test for fairness, we don't need to know which outcome is correct, as long as the two outcomes are the same. Now, that doesn't preclude correctness testing, which very well may care about which outcome is correct, and which, of course, systems must still undergo. But for the sake of fairness testing, only consistency of outcome is important. And this makes causal testing very powerful, because we can automatically generate lots of inputs, and we get the oracle for free, so we can fully automatically test software for causal bias. We built a tool called Themis, named after the Greek goddess of fairness, for automatically generating test suites to measure discrimination. Themis works on categorical inputs, which makes it relatively easy to manipulate sensitive attributes, though we and others are working on expanding the ideas to other types of attributes. Themis is open source at fairness.cs.umass.edu. Themis allows you to answer questions such as, how much does my software discriminate with respect to a specific attribute, and does my software discriminate above some threshold, and against what? Of course, if you run a piece of software on every possible input, you can measure many of the definitions of fairness I've described, but running every possible input isn't feasible for reasonable software. So Themis does several things for efficiency. It uses adaptive, confidence-driven sampling to know when to stop generating tests, and it uses provably sound pruning to reduce the number of tests needed to measure some discrimination. I won't go into more details here, they're all in the paper, because I'd like to focus on our findings. We procured two datasets for our evaluation. One is the census income dataset of 45,000 people's financial data. We use this dataset to predict if a person's income is above or below $50,000. The second is the Statlog German credit dataset of 1,000 people's credit data, each labeled as good or bad credit. We then got 8 open-source machine learning systems off the internet. Some of these are standard machine learning, part of the scikit-learn toolkit. Others are designed specifically to avoid bias in learning. Those come from the papers I showed you earlier, and all attempt to minimize demographic parity. Note that all these systems are basically machine learning packages, and our goal here isn't to show that one is better than another. We're approximating testing real software by training these models on these datasets, and our goal is to see if Themis can effectively catch bias. The source of bias isn't particularly important in this study. At the high level, we trained a bunch of systems, and some are supposed to enforce fairness, while others are not. So, what did we find? We found, as expected, that demographic parity is not nearly enough to catch bias in software. In one example, a decision tree system trained specifically to optimize gender demographic parity did so, but experienced 0.11 causal discrimination with respect to gender. This means that for 11% of the users, just changing their gender and keeping everything else exactly the same changed their credit label from good to bad, or vice versa. So what's going on here? Well, it's exactly that fairness gerrymandering phenomenon I told you about. Machine learning finds a way to slice and dice the data to maximize whatever you ask it to maximize. And if your data has bias in it, and you don't explicitly ask it to avoid a particular kind of bias, well, you get bias back. To paraphrase Army Specialist William Mellon, bias in, bias out. Except that I'll show you later in the talk that, unlike with garbage, you can actually have bias go in and fairness come out. Next, we found that using the algorithm that optimizes demographic parity can inadvertently introduce other bias. For example, we had a system that was trained to optimize demographic parity with respect to gender, and that ended up significantly increasing discrimination against race, up to 38%. Again, the observation is that if you don't specify for your system exactly what to enforce, it has no reason to enforce it. So specifying the requirements properly is critical for software fairness, as it is for any other desired software property. Finally, we found that our pruning techniques were quite effective, reducing test suite size by 148 times on average for causal testing and over 2,800 times for demographic parity. Causal testing is a powerful idea for discrimination detection, but it actually goes well beyond that. Causal testing is also powerful for finding traditional bugs. We have a paper in ICSSE 2020 on using causal testing to debug. The central idea is that to a developer, seeing two nearly identical test inputs, one that passes that oracle and the other one that fails, can be very useful. Seeing these causal pairs can point to precisely the cause of the defect. Imagine seeing one buggy execution for an online shopping portal with a large cart full of items and lots of shopper information as input, and this execution results in an error that says illegal purchase, and now you have to hunt down the cause of that error. Now imagine seeing the exact same execution coupled with another one that shows that if everything else is kept exactly the same, except the shopper's birthdays changed to make them over 18 years of age, the execution no longer results in the error. I'll focus on fairness today, but if you're interested in learning how causal testing can help hunt down traditional bugs, take a look at our paper, Causal Testing, Understanding Defects' Root Causes. Let's get back to software fairness. Testing goes hand in hand with debugging. Themis not only measures causal discrimination and other kinds of discrimination, it also produces causal pairs that evidence the discrimination. Developers can, in theory, use these pairs to examine their data, perhaps augment the data, or to help understand their system's logic. There have been several papers published building on Themis, looking at improving the efficiency of finding these causal pairs. Udeshi and co-authors had a paper in ASC 2018 on directing the search for causal pairs, and Zhang and co-authors have a paper in ICSSE 2020 on using gradient-guided search for the same purpose, which they show works better for deep learning. And looking more at debugging the underlying data to produce more fair systems, Salimi and co-authors built Capuchin to understand data relationships to modify the training data. Debugging is, of course, an important aspect of the software engineering lifecycle, and one that requires more work to produce tools to support developers building fair software. Thus far, I have focused on software that has categorical inputs, such as loan applications on which race is listed explicitly. This makes it somewhat easy to modify the sensitive attribute without changing anything else. But there are numerous more complex cases. For example, the attribute of interest might not be explicitly included in the input, or other attributes might correlate with it. What we have done so far is a conservative approach, If Themis says that a system causally discriminates, then it definitely does. That is because Themis has found inputs for which changing one or more sensitive attributes, such as gender or race, directly affects the output. But Themis is incomplete. It is possible that a system discriminates, but Themis doesn't see it. This can happen if there are correlations between the sensitive attributes of interest and other attributes. But when Themis modifies the sensitive attributes and doesn't modify the others, the discrimination doesn't surface. Here's a simple example. There's a correlation between gender and hair length. Suppose a loan program looks only at hair length to decide if to approve a loan. Two people of identical hair length, regardless of gender, would either both get the loan or neither get the loan. So Themis would claim no causal discrimination. And Themis is right, kind of. The problem is that when applied to a real population, the loan program, in practice, will make decisions based on gender. It is possible to overcompensate in the other direction. Themis could project the other attributes using their correlations with a sensitive attribute, as, for example, others have done. This could catch more bias, but the measurement is no longer sound. That is, it could identify bias in a system that doesn't exhibit it. A more challenging problem is handling continuous, semantically complex inputs. Let's take a look at another example of bias in software. ACLU did a study of Amazon's facial recognition software. Until recently, law enforcement in America was using this specific system. ACLU found that the system discriminated. So what does it mean to discriminate in this context? Facial recognition is a hard problem, and you cannot expect the software to be correct every time. Here, ACLU found that when the software did make mistakes, the false matches were disproportionately people of color, including 6 members of the Congressional Black Caucus. This measure of bias is a correlation-based measure. It measures and compares the number of false positives in each group. This is not causality, which of course is still discrimination and still important to measure. But I have argued that measuring causality is an important aspect of building fair software. What would it even look like to test facial recognition for causal bias? You'd have to create images of people that are identical in every way except a sensitive attribute, such as race or gender. Well, researchers at NVIDIA are working on just that. I'm showing here results of a GAN generating images of faces. If you haven't been to thispersondoesnotexist.com, I highly recommend it. It's a great way to lose half an hour of your life. These faces are incredibly realistic, but they're not of real people. They're generated. The idea is to train from real faces, embedding them in a latent vector space, such that every point in that space can be decoded into a face. You simultaneously train a classifier that tries to decide whether the decoded face is a real image or a computer-generated one. Taking this adversarial approach, you keep training your encoder and decoder together until they fool the classifier into thinking the generated images are real. So, take a close look at these 2 rows of images. In each row, if you look at the images in the middle, there are gradual projections between the leftmost and rightmost images. It's not perfect. There's some more abrupt changes in some adjacent pairs than others, but you can clearly see the trajectory. What's happening here is that the leftmost and rightmost faces are points in that latent vector space, and if you draw the line connecting those 2 points, sampling points along that line are the interpolations between the 2 faces. There's something kind of strange happening here. Let me give you a moment to see if you can catch it. Did you find it? These 2 faces are identical, so these 2 lines in this multidimensional space happen to cross. This is very promising technology, but they're all fake generated faces. Some folks have been working on embedding real faces into this latent vector space to then project between real faces. This can lead to changing higher-order attributes of faces, such as gender or race. That's hard work, and each step, embedding the face, computing the trajectory, decoding the intermediate images, adds some noise. So we're not quite there yet to be able to modify high-level attributes, but we're making progress. And there are many people working on a similar problem in natural language processing. There, the problem is called style transfer. There are some promising results, but again, we're not there yet to test real-world systems. Testing systems is an important part of building high-quality software, but I promised you up front that I would talk about provable guarantees and using fairness-verified components. So let's talk about that. Let's focus today on machine learning because, as has probably become clear from my talk, while it's not the only way to inject bias into software, today it happens quite often. So, How would you build a machine learning, let's say classifier, that can train on data without knowing if that data has bias, but produce a classifier that can guarantee that on unseen data it would satisfy a fairness property of your choice? Let me tell you about our approach. We call it the Seldonian framework for designing machine learning algorithms. The user specifies a definition of fairness. This is important because if you build machine learning tools, they should be usable by domain experts, and it is those domain experts who understand what fairness means in their domain. So they need to be able to specify a definition, and your algorithm needs to respect that definition. I'm going to describe the rest of the approach at a fairly high level. We split the available data into 3 sets: a training set, a testing set, and a safety set. We train classifiers in the training data, and we use the testing set to produce one we believe is likely to satisfy the fairness definition the user provided. To do that, we use confidence bounds, such as Hobding's inequality or t-tests, when we know the data come from a normal distribution. We produce our best guess at a classifier, and then we use the safety set, once and only once, to check if the fairness property holds. Now, here's the important bit. For our approach, in fact, for any fairness guaranteeing approach to work, it has to be able to say, I can't do that. I couldn't produce the classifier you wanted. If someone ever tells you that they produced a machine learning algorithm that guarantees to satisfy some property, such as fairness, on unseen data, but it always returns a solution, don't believe them. Because what happens if I give you only 10 data points to learn from? You cannot generalize anything from 10 data points. You cannot produce a classifier that guarantees anything from 10 data points. But the way machine learning usually works, if you give it data, any amount of data, it does its best. Our approach, if the safety test fails, says,
I'm sorry, Dave. I'm afraid I can't do that.
This might happen if we don't have enough data, if the algorithm gets unlucky, or if the user specified fairness property or properties that cannot be satisfied, which is actually a serious problem. Many of the definitions of fairness I mentioned to you earlier cannot be simultaneously satisfied. There are several papers on impossibility results with respect to these definitions. Now, impossibility of satisfying requirements is nothing new for software engineering. I can easily come up with usability and security requirements that contradict one another. But, again, we need tools to help developers understand and handle these contradictions among fairness requirements in software. So, let's take a look at how well our Seldonian algorithms do. What you're looking at is a graph of a whole slew of classification algorithms trying to learn a model. On the y-axis is the fraction of the time the learned classifier violates a disparate impact requirement, which is indicated here by the dotted black line. To satisfy the requirement, the system should stay below the black dotted line. On the x-axis is the amount of training data the algorithm has access to. The red lines are all standard algorithms that don't try to ensure fairness. Note that they usually do pretty poorly, though sometimes by sheer luck they do okay. Our Seldonian algorithms are green. Note that the green lines never violate the requirement. They could, actually. Our guarantees are based on confidence bounds, so they're probabilistic, but we can make our guarantees hold up with arbitrarily high probability. The blue fair learn lines and the purple fairness constraint lines are 2 learning algorithms that attempt to learn fair models. But, as you see, they can fail, either because there's insufficient data for them, or because they fail to encode disparate impact. I'll show you in a minute what happens with other definitions. This graph tells only part of the story. Recall that the price of using Seldonian algorithms is that they can fail to return a solution at all. The middle graph here shows how often that happens. For small training data sets, quite often. The dashed green line is using Hobding's inequality, which is more conservative. The dotted green line is using t-tests. Note that for beyond a pretty small training set size, the Seldonian approaches almost always return a solution. The other approaches, of course, always return one. Now, an important question to ask is whether enforcing fairness sacrifices accuracy. We find that in real-world datasets, the answer is typically no. The left graph shows the classifier accuracy. Note that for training datasets above 10,000 points, the Seldonian solutions do just as well as the best algorithms, even those that don't try to optimize for fairness. But as I mentioned, the Seldonian approach allows the user to specify the definition of fairness, or even multiple definitions. In fact, the user can also specify safety definitions, such as that one medical device cannot cause more harm than another device. But that topic is for another talk. Here's how our algorithms perform with demographic parity and equal opportunity. Some of the competitors do a little better, but we still guarantee that we satisfy the requirement, and our accuracy is still maxing out for the larger training sets. Equalized odds and predictive equality. Same story. I didn't have time to go into all the details. To read more about our work, check out our paper in the December 2010 issue of Science. I want to thank my sponsors and my large group of wonderful collaborators. I want to particularly highlight Phil Thomas, who was the driving force behind the science paper and the Saldonian framework, and Alexandra Melu, who had the initial ideas related to fairness in software and got me involved in this entire effort.
I hope my talk today has demonstrated that bias and discrimination in software are an important problem, and that software engineering is one of the places that can help solve this problem. I also hope that the talk has encouraged you to go out and work to solve this important research challenge. I want to thank one more time the organizing committee for giving me the opportunity to give this keynote address, and I look forward to learning about all the new exciting research results from the research community. Thank you.